Okay, so let's talk about where we're at. We have a roadmap for where we're going, and so there's sort of 4 stops along the way. We started last time by talking about sequences, and we're going to talk about that a little bit more as we go on. But the way we should think about sequences is a sort of an infinite list. And that's not so bad. It's like you have a lot of numbers. You know, it's the dot, dot, dot. Today, we're going to talk about series. And so what is that? Well, now we're going to add up an infinite list. So it's actually like, well, we have a whole bunch of numbers. Let's add them up. So it's plus dot, dot, dot. See, that plus, that's going to be our challenging part for today. And our long-term goal is to be able to say, well, what happens when we add things up? Now, tied to both sequences and series, there's a really fundamental question. And that question is, when do we know when things converge? And you can see, you know it's fundamental because it says it right here. And this is one of the things that makes this particular course a little bit more interesting, or perhaps more challenging, depending upon how you see it. You see, in the past, we work on a problem, and like, we work, there's an answer, a number, we got it. But now we're going to start entering into a phase where we're like, work, and we know there's a number, but we don't know how to get the number exactly, but we can tell you how to approximate it, we can tell you whether or not there should be a number. It seems a little bit less satisfying, but we have to sort of understand that we're getting to sort of the phase of, is there an answer? Which is a different type of a question. And so we're going to be spending a lot of time talking about when do things converge. And that's the big theme for the next couple of weeks. Now there's a special case that's very useful to know, and we'll mention it here. And that's when things are what's known as monotonic. Now we've actually seen that word before in Calc 1. So mono, that means one. And tonic is a type of drink. So you require one drink to understand this. No, that's not what it means. Tonic, you should think of that more as behavior. And so one behavior. So when we talk about monotonic, we mean things that are always going up or always going down. So the behavior is, are you increasing or are you decreasing? And here's a nice result. And we're not going to prove it, but it says the following. If we have something which is monotonic, and let's say increasing, and it's bounded above, then it must converge. Well, what does that mean? Think of it as you have numbers on a line. And what do you have? Well, somewhere way out here, you have a bound. So you say, look, this is a bound. I can never go above that point. Now, I don't necessarily mean I go to that point, I just mean it's a bound. And I'm going up. So I can think of my numbers as being points on my line. And they might be somewhat sporadically spaced, but eventually I can't go too far and I have to converge to something. Again, I may not know what that something is. Sometimes I do, sometimes I don't. But we'll get into the practice of talking about these things. Let's do a really simple example. So suppose we have the sequence a sub n, n goes from 0 to infinity. That just tells us where indexes are. And we have a0 equals 0, and then the next term, remember this is like a recurrence. So how do you get to the next term? Well, you take the square root of the current term and add 2. So we want to show that the sequence converges by showing that it's at most 4 and that it's monotonic. And then the question is, well, what does it converge to? Now here, we'll actually do a sort of an argument by picture because, well, I like pictures and I feel it helps me understand things. So let's think about this. So what do we have? We have that if I want a sub n, I can think of it as the square root of a sub n minus 1 plus 2. Another way to think about this is suppose we think of this as a function. Well, what function are we talking about? Well, let's have our function, think of our a n minus 1 as being our input, That's square root of x plus 2. So what we get then is that a sub n is f of a sub n minus 1. So in some sense, I'm trying to understand what this function is doing. So let's sketch this function. So square root of x would normally look like that, the square root function. The plus 2 says go up to 2 and then start going up. Okay, so there's our square root. Now, what do we want to do? We want to show that we are increasing, right? So we want to show that if I look at my next term, a sub n, then that's going to be less than or equal to what happens when I plug a sub n into my function. In other words, I want to compare how does my current term compare to my next term. That's current, that's the next term. Well, this is the function square root of x plus 2. What would this function correspond to? Well, that would be the function here. This would be the function of just x. In equals out. So, what do we have? Well, square root of x does something like that. Now, you might pause for a second and say, where do these two intersect? Well, what happens? Well, when does x equal the square root of x plus 2? Now, there's lots of ways you could solve this. One way you could do it is you can do a little bit of rearrangement. X minus square root of x minus 2 equals 0. You might say, that's kind of a weird equation. But then you can think, oh, that's really like square root of x squared minus square root of x minus 2 equals 0. And that factors. Because, of course, it's calculus. Everything factors. Do you see what it factors as? Square root of x minus 2 square root of x plus 1. Well, of course, that doesn't make any sense. Square root of x won't be negative 1. So here's where it makes sense. So that would be at square root of x minus 2 equals 0, which happens at x equals 4. So this point over here is at 4. Now, what's the moral? Well, what we have is let's take a look at a couple of things and convince ourselves that it's true. So, we need to argue that a sub n is at most 4. So that says I can never go above 4. And, well, it's true that, look, if you put any number below 4, any number at all, see, your output is here. So if our input is less than 4, our output is less than 4. Because if our input is in here, if here's our input, our output is in here. So, since we started less than 4, we have to stay less than 4. Because no matter where we start, we always end up less than 4. Okay. Now, why are we monotonic? Well, notice that the a sub n, if here is our a sub n, there is a sub n, and there is f of a sub n. And because the line y equals x is below the line y equals square root of x plus 2, then it must be the case that a sub n is less than or equal to f of a sub n. All right. Now, this is a little bit fun, but all right. What does it converge to? Well, here's the picture. We started at 0. So, when I plug 0 in, what's my next term? Well, it'd be square root of 0 plus 2, which is 2. Now, the way to get it in the picture is you go up to the curve. That's your next term. Then you go over across. All right. So if this is a0, this is a1. Now, how do you get a2? Well, plug a1 in. Go up, go across. So there is A2. How do you get A3? Up, across, and up, across, up, across, up, across. What's happening? We're zooming in to the intersection. And that's what's going to happen. So we need to find where do these curves intersect. And the answer is they intersect. We found that. They intersect at 4. So we get that A sub n converges to 4. Now that's a picture. What if we didn't have a picture? Could we do it without a picture? And the answer is that, yeah, we can do it without a picture. So here's what you do. So what you do is you say, all right, let's suppose A sub n converges to something. And for a second, we'll give it a name. So since it's converging, let's call what it converges to L. So we're going to say A sub n converges to L. Now, what do we have? Well, look on this relationship here and just say, let's let n get big. So dot, 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 we let n get big. What does A sub n get close to? Well, as n gets big, A sub n gets close to L. What does the square root of A sub n minus 1 get close to? Well, the square root of, what is A sub n minus 1? Now remember, A sub n is getting close to L. So what does A sub n minus 1 get close to? The answer is L. It's not L minus 1. No. Look, this is just, this term, A sub n, is right next to that term in the sequence. They're next door neighbors. And what's happening is if something's converging, then at the end, everything near the end looks about the same. So this will also be very close to L. And then plus 2. And now what we have is we have a relationship that we can solve. And it's the same relationship we have down here. And we actually did solve that. We got 4. So that's sort of the algebraic way. This is the geometric way. And so that's how we can find these things. All right. Now, let's get back to the real topic for today, which is series. So we need to talk about adding things up. So what we're going to do is we're going to say, all right, we start adding A0 plus A1 plus A2 and so forth and so on, plus AN, plus, of course, the dot, 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 dot. That's the hard part. Now, how do I know it's the hard part? Because it says it right there. See? Hard part. So it must be hard. Well, why is it hard? Well, the problem is you can't actually add infinitely many things together. It's impossible. And so how do we do it? If we said we can't do it, so how do we actually do it? Well, the answer is we look at what it should be. See, it's the same way with sequences. When we talked about sequences, we said, look, you got A0, A1, A2, and then you keep going. And we said, well, what's the end? What does it approach? Well, it's not like we go to the end of the list and like we picked up, hey, I have A infinity, and it looks like it's about that. You can't do that. So you can't add up infinitely many things. So you can't look at the last thing on an infinitely long list. But what you can do is say, what should it be? And that's the beauty of math, is you can say, all right, even if I can't actually do it, I can say, here's what would happen if we could do it. So the way we do it is instead of trying to add up infinitely many things, we add up just a couple of things. So finitely many things. We call these partial sums. So what we're doing is we're going to add up this whole infinite list. We say, well, look, let's just add up the very first term on the list. Well, that's easy. How about the first 2 terms? A0 plus A1. Easy. Next, first 3 terms. A0 plus A1 plus A2. Cool. Great. All right. And so forth and so on. So we have that Sn. Now this is a number. These are numbers. S0 is a number. S1 is a number. S2. All these are numbers. And what they correspond to is partial sums. A0 plus A1 plus dot, 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 plus An. It's the sum, k equals 0 to n of A sub k. So probably we should review our sum notation, right? So this is a sigma for sum. So it's easy to remind. Sigma is for sum, that's what it means to me. Sigma is for sum, that's what it means to me. Sigma is for sum. That's what it means to me. Sigma, sigma, sigma is for sum. So, whenever you see a sigma, it means you're adding things together. The K, what is that? That's called our index. And that's, when we're compressing it, we need to have something that keeps track. The 0 here is where we start our sum. The N is where we end our sum. And of course, the A sub K is a formula or an expression for the kth term in the sum. And you'll notice that it should depend on the index. So the index is kind of a dummy variable, and you can change it without actually changing what your sum is. So now what we have is we had an original sequence of these A0, A1, A2, so forth and so on. We created a new sequence of the partial sums. So now I have a new sequence, and I ask the question, what happens to that sequence? Well, maybe it converges, and maybe it doesn't. If it does converge to L, so in other words, the partial sums go to L, then we know what the infinite sum should be. And we say that the sum from k equals 0 to infinity of a sub k should be L. So we say it equals L. All right, well, let's try this. Let's find a sum. So find the sum, n equals 0 to infinity, of 1 over 2 to the n. Well, let's start by writing down some of these partial sums. So S0. So that would be 1 over 2 to the 0, which is also known as 1 over 1, which is 1. Okay, that wasn't so bad. All right, well, one partial sum down, infinitely many to go, right? Well, that's the problem with infinity. It takes you a while to get going. So the next, S1, so that says going from 0 to 1. And so I'll have the 1 over 2 to the 0 plus one more term, 1 over 2 to the 1. So it's actually the same as before, 1 over 1 plus 1 over 2, which is 3 over 2. All right, how about S2? Well, 1 over 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 squared. That's 1 over 1 plus 1 over 2 plus 1 over 4. All right, what does that go to? Well, we could get common denominator of 4, 4 fourths, 2 fourths, 1 fourth, and that would be 7 fourths. Another way to think about it is like, look, it's like I am taking the previous sum, I'm just adding that one more term. One more term. What could that do to it? Well, hopefully not too much. S3, so 1 over 2 to the 0, 1 over 2 to the 1, 1 over 2 squared, 1 over 2 cubed. Whoops, there we go. 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 8, which gets us, okay, just think about adding 1 over 8 there. So that would make that 14 over 8 plus 1 over 8 makes 15 over 8. How about one more? S4. All right, 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 to the 2 plus 1 over 2 to the 3 plus 1 over 2 to the 4, which is 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16. All right, well, let's see. That would be 30 over 16 plus one more term, 1 over 16, gets us 31 over 16. Now, at this point, we can keep going, but it's better to try to spot the pattern. Do we see a pattern emerging? Like 31 over 16. That's not such a strange number, is it? Like 31 over 16. What is that about? Well, notice that 16, if you were to double that, would be 32. So this is almost 2. How almost 2 is it? Well, it's really 2, but then I'm just a little bit short. Minus 1 over 16. How about 15 over 8? Again, if you double 8, that's double 8. You get 16, so we're just off. Well, that's 2 minus 1 over 8. Well, let's see if that still holds. So what would this term need to be? So that was 1 over 16, that's 1 over 8. 1 over 4, does that work? Is this 2 minus 1 over 4? Yeah, it works. How about here? That would be, let's see, 6 and 8, a half, right? 2 minus a half? Is that? It is. It works. How about the very first term? 16, 8. It'd be 2 minus 1. And it works. Okay, good, good. So it looks like we have a guess. What's our guess? It says our nth term of our sum looks like 2, right? It's 2 minus something. Well, minus what? Well, in the fourth term, it was that 1/16th we were off by, which is that 1 over 2 to the fourth. The third, this has 3, is that 1 over 2 cubed we were off by. As 2, 1 over 2 squared. So it looks like 1 over 2 to the n. Now, currently, we should say that this is our guess. Now, we would like to do more than guess. If this were a different kind of class, we would say, can we do better? The answer is you can do better, and let's just talk about what would happen. So this next couple minutes is for fun. Fun math education. It's good to learn stuff, right? So how would we argue? Now, some people might use the word prove, but oftentimes when students hear the word prove, they're like, proofs? No, I don't want to prove anything. But if I say argue, it's like, oh, good, I like to argue. So how would I argue that this is correct? Well, one way is to check, is it correct the first time? And, well, let's check. If we plug in 0, we get 2 minus 1 over 2 to 0, which is 1. Yep, that works. Okay, good. Now, why is it important to know it's true the first time? Well, we want to show it's true every time, so we should argue that it's true the first time. Now, the next thing that's going to happen is we're going to say, well, is that enough to know it's true the first time? Well, here's what I like to think of it as. So what we're going to do is we're going to work our way up. So instead of trying to argue every single case, because that would take a very long time, infinitely much time. So what we don't want to do that. What we want to do is say, look, we know it's true the first time. Good. So let's argue if it's true one time, it's true another time. So that's sometimes, there's a fancy word for this. It's called induction, which is if you can prove it's true the first time and also show if it's true one time, it's true every time thereafter, then that's enough to show it's always true. So let's check. So what do we have? Well, what we do is we look at our next case, right? So that would be our Sn plus 1. Well, what does Sn plus 1 look like? Well, actually, we kind of see what it looks like. You see, when you can come over here, when I look at S1, it's just you add on one more term. You look at S2, you add on another term. And when I say you add on another term, compared to the previous case. So your Sn plus 1, it's always your Sn, the sum of what you already looked at, plus one more term. So that's what it always behaves like. Now Sn, well, we know what that looks like. That looks like 2 minus 1 over 2 to the n. See, that's our guess. What is our next term, that a sub n plus 1? Well, in our case, this is our generic form of what a sub n is. So a sub n plus 1 is 1 over 2 to the n plus 1. Now, if you add these together, what do you get? The answer is 2. All right, that wasn't surprising. Now, if I want to get common denominator, well, I want to make it 2 to the power n plus 1. So I multiply this by 2 over 2, which makes it 2 minus 1 over 2 to the n plus 1, which is correct. That shows that once one case is true, the next case is true. And we know the first case is true, which means all the other cases are true. So no, this is not just a guess. We've upgraded. This is now correct for all n. Good. Now, are we done? Well, we're not quite done yet. What we've done is we figured out there's a pattern for these partial sums. Now the question is, what does this converge to? Well, so we take the limit as n goes to infinity of 2 minus 1 over 2 to the n, and say, well, what happens? Well, the 2, that's easy. That's always 2. The minus 1 over 2 to the n, well, that 2 to the n is going to get a huge number in the denominator. 1 over a huge number is a small number. So that's going to give us 2 minus 0, or 2. So our partial sums converge to 2, and therefore we come to the thrilling conclusion that that sum is 2. And there we go. All right. Now, we'd like a more efficient way to do these problems, and we are going to do it. In fact, this is just sort of to illustrate the type of ideas coming up. So let's talk about series that are kind of like this. Now, what do I mean by kind of like this? You see how it's like 1 over 2 to the n? There's that to the nth power. And so we're gonna take a look at series like that. And they have a special name. And they're called geometric series. So when you hear the word geometric, you should always think of there's some kind of multiplication happening. So there's two types of things that you often encounter. One term is arithmetic. Arithmetic is a fancy way of saying we're going to add things. Geometric means we're going to multiply things. We're going to multiply things together. So when we talk about a geometric series, or geometric sequence really, that says if I want to know what my next term is, I take the current term and multiply it by some fixed number. So what happens is I start with my first term, let's call it a. And then the next term I multiply it by some number r. Think r is like a ratio here. So a times r. The number after that, well, multiply by r again, ar squared. The number after that, ar cubed. The number after that, ar to the n, and so forth and so on. So in general, what we have is that the terms look like a times r, which is some fixed number, to a power k. We're going to add that up. K equals 0 to infinity. All right, so how do we do it? Well, let's actually just work through an argument that we'll cover sort of all cases. We don't want to go through the argument we did on a case-by-case basis. We want to find a simple way to do it. So the key is when we're talking about series, adding these up. So when we say a geometric series, it means we're adding up a geometric sequence. We say, okay, let's look at our partial sums. So if I look at the Sn, that says, look, I'm going to go, and then I stop. All right, good. So our goal is, what is that Sn? If we can figure that out, then we can take the limit. Now, here's what we're going to do. It's kind of a fun idea. To say, you know, these terms, consecutive terms, are very similar to each other. They just differ by a factor of r. So let's multiply everything by r. So if I multiply both sides by r, we'll get r times Sn is equal to a times r, right? Because a times r gets us ar squared, right? Because that multiplied across, the ar squared goes to the next term, so forth and so on. The previous term multiplies to ar n minus 1, then you get ar to the n comes from that a to the power r to the n minus 1, and then you get sort of a new term on the n. So in essence, what happens is when you multiply it by r, you did a shift over by 1. And now you look at these things and say, wow, they have so many things in common. Well, when you have lots of things in common, that's a good sign that subtraction will make things easy, because that helps you cancel the stuff out that's common. So we subtract. On the left-hand side, we get 1 minus r times your sum Sn. The a, well, that didn't cancel, but then the beautiful thing is lots and lots of cancellation, right? The ar's cancels, the ar squared cancels, the dot dot dots, the ar to the n minus 1, the ar to the n's. What doesn't cancel is this other term on the n. And remember, that's the part that we're subtracting. So it's minus a to the power r to the n plus 1. So what's ended up happening here is we had a lot of terms, but then we canceled it, and then we only had a few terms. And that's really good. We like it when there's fewer things to worry about. So we can now divide by 1 minus r. At least we can, as long as r is not 1. In the case when r equals 1 is a very uninteresting case, so we don't worry about that. So the partial sums look like a minus a to the times r to the power n plus 1 over 1 minus r. All right, now what's our goal? Our goal is to figure out what happens to our partial sums. Now the beautiful thing is that we've taken our partial sum and reduced it down to a very small expression. So the only thing left to figure out, look, the a, that's a number, that's fixed. 1 minus r, that's a number, that's fixed. So nothing's going to happen to those. So, all right. So the only thing that could change is this thing here, this r to the power n plus 1, right? Because that's the only place where n is showing up. So we need to get a handle on that. All right, well, last time we actually talked about this. We said, hey, if r is small, then r to the n goes to 0. So if r is small, so let's assume r is small, then what happens is that this part here goes to 0, and we're left with a over 1 minus r. And that's our answer. So for r small, we have that the sum from 0 to infinity, ar to the k, is a divided by 1 minus r. And that is good. In fact, you can see there's a box here. That means it's an important thing to remember. In fact, we'll put another box around that box because it's a really good box. In fact, not only are we going to put a box around that box, we'll box that box. So it's been double boxed. And not only that, we'll add a little bit of a star here because this is an all-star formula. And if we were to go even crazier, we could say, well, maybe it's a shooting star. All right? So you can probably tell from all that we've talked about that geometric series, they're important. Very, very important. In fact, they're sort of the backbone of a lot of the arguments we're going to be talking about later on. So it's really important to understand how these work. Now, another way to think about what's happening here is you should really think of the following. If you come back to this expression here, what does a correspond to? Well, a corresponds to the first term. So if you ever have a geometric series, there's two things. What's your first term? And that's what goes on top. So the first term is the top term. All right. Well, what is r? Well, r here is your ratio. And that's what you multiply at every stage. So that's what goes there, your ratio. So if you ever have any geometric sum at all, doesn't matter what it is, you always say, okay, take your first term, divide that by 1 minus what's your ratio? And the ratio is what you're multiplying by at every stage. All right, well, let's do this one. Find the sum, n equals 0 to infinity of 1 over 2 to the n. You might remember we did this one a few minutes ago, and it took us a while, but now we have a formula. So first question, is this geometric? Right? You should always ask yourself. You know, we don't apply a formula unless we know it's the right formula to apply. Now, one way we can write this is the sum n equals 0 to infinity of 1/2 to the n. So we can think of it that way. And we can even, if it helps, we can say, look, it's really like 1 times 1/2 to the n. Now we're like, okay, yeah, it really looks like this, right? Now, you might object and say, no, Steve, it doesn't look like that. This has a k, that has an n. Clearly, they're very different. But actually, they're not that different. So you see, this is an index. And indices, you can modify them and change their names to be whatever you want. Whatever's convenient. So if it's confusing you, you can say, look, I'll just replace all my n's by k's. Life is good. It's the same sum because you're still adding all the same things together. So anyway, so what does our formula say? Well, what's our first term when you plug in k equals 0? Well, k equals 0, well, 1 times 1/2 to the 0 is 1. So first term goes on the top. Divided by 1 minus, what's our ratio? Well, that's the something to the k. Now be careful here. You might think, oh, should it be 2? But no, it's, see that, because that's downstairs. So it's 1/2 to the power k. So our ratio, everything we're multiplying at every stage by 1/2. So that's 1 over a half, which is also known as 2. And that's pretty good. That's pretty short, actually. That took almost no time at all. Well, let's try some more. All right, so let's do some more problems. Let's find the sum, k equals 0 to infinity, of minus 2 to the k over 5 to the k. Okay, well, what can we do? Well, let's rewrite this. So the sum, k equals 0 to infinity of, well, I want to think of this as geometric. So the question is, what do we multiply each time? Do we multiply by -2 each stage, or do we multiply by 5 at each stage? And the answer is yes, we do. We multiply by both. So a better way to write this is as minus 2/5 to the k. Okay, so now it looks like a geometric series. It's something to the k power. There's not a constant in front, so you can assume that the constant is 1. Can we apply our formula? The answer is yes. Why? Well, note that if we take the absolute value of -2/5, that's pretty small. So that means we can apply our formula. So what do we get? Well, what's our first term? That would correspond to when k equals 0. And so that would be anything to the 0, other than, of course, 0. 0 to the 0, that's a fun question. But something to 0 is 1. Divide that by 1 minus, okay, what do we multiply by at each stage? And the answer is -2/5. So minus minus makes it a plus. This will be 5/5 plus 2/5, so this is really 1 over 7/5, which is the same as flipping the 7/5 over 5/7. And that's our geometric sum. All right, good. Now, that wasn't so bad. These are pretty easy. Find the sum, j equals 3 to infinity, of 3 to the j plus 2 over 4 to the j. Now there's a couple of ways we can do this, and well, let's just talk about it. Now, one of the things you might say is, oh, there's a problem. These exponents don't match. See, one of them is a j, one of them is a j plus 2. But what we can do is we can do the following. We can say, hey, we can break things up. Because whenever I have something to the power j plus 2, that's the same as saying 3 to the j, 3 to the 2. So addition in the exponent becomes multiplication. Downstairs, we just have 4 to the j. And we can rewrite that. That's the sum, j equals 3 to infinity. 3 squared, well, that's 9, I guess. And then 3 to the j over 4 to the j makes it 3/4 to the j. Okay, so can we apply our formula? Now, we don't check the size of the 9, because the 9, it's never changing. The question is, what are we multiplying by? We're multiplying every stage, we multiply by 3/4. Is that smaller than 1 in absolute value? And the answer is yes, which means we can apply our formula. Okay, so according to our formula, this would be equal to, the downstairs will be 1 minus 3/4, right? Because that's what we multiply by. Now you'll notice I started with the downstairs. Now what goes upstairs? Is it 9? And why not? Okay, let's be careful. It feels like it should be 9, right? Because we said, okay, you know, what happens? But do you notice something different about this problem? Look at where we start. We're not starting at 0. We're starting at 3, which means that our first term doesn't correspond to j equals 0, which would be 9 if j were 0. It corresponds to j equals 3. So we have to plug 3 into here. So that would be 3 over 4 to the 3. So this is the first term in our sum. Now we can clean this up. 1 minus 3 over 4 is also known as 1/4. And so you get 9 times 3/4 cubed divided by 1/4. Well, you can flip that 1/4 over. So let's see. Well, let's clean this up. So what do we have? We have 9, which I can think of that as 3 squared. This cube, I can write that as 3 cubed, 4 cubed, and then this 1/4 comes up as a 4. And so if you finally clean that up, you end up with 3 to the 5 over 4 to the 2. Now, of course, we all know that 3 to the 5th is 243, and 4 squared is 16. But, you know, common knowledge, not surprising at all. All right, so there's our answer. Now, be careful here. Be careful here. So you always want to make sure you get the first term. Now you might say, I'm not comfortable with starting at 3. Can I do anything about that? And of course, we're going to tell you that the answer is yes, because we're here to say, look, there's options. There's many options, always. There's something. So what we can do, if you want to insist, I really want to start at 0. So you can do what's called reindex. Now, reindexing is kind of like substitution, but for sums. So what do we want? Well, what we want is we'll come up with a new index. We'll call it k. Now, what's the key? Well, we want to have our sum start at 0. So we want it to be the case that when j equals 3, that should match k equals 0, right? Because that's what we want. We really want to start at 0. So we have to think about, well, what's a rule that does that? So one rule that does it is that we're going to say, look, we're going to let k be equal to j minus 3. All right, so there's our, again, think of this as a substitution. So what do we get? Well, if we think of our original sum, we'll write it down again just so we can go through it term by term. J equals 3 to infinity, 3 to the power j plus 2, divide that by 4 to the j. Now, everywhere where I see a j, I've got to do a replacement. So, this will be a sum. K. Now, when j equals 3, what does k equal? It equals 0. Don't forget the upstairs. When j equals infinity, what does k equal? Well, turns out infinity minus 3 is still infinity. Another way to think of it is, as j gets large, k gets large. All right, well, how about this? 3 to the power j plus 2. Well, look, I can solve for j. J equals k plus 3. So this becomes 3 to the power k plus 3 plus 2, which is k plus 5. And downstairs, 4 to the k plus 3. All right, good. Now, what happens next? Well, again, let's break up our exponents. So sum, k equals 0 to infinity, and we would have 3 to the k times 3 to the 5, downstairs 4 to the k times 4 to the 3. So we can do one more rewriting, sum from 0 to infinity, and this would be 3 to the 5 divided by 4 to the 3 times 3/4 to the k. And now we apply the rule. So now we're like, hey, look, now we do start at 0. What's the first term? Our first term is 3 to the 5th divided by 4 cubed. Divide by 1 minus r. And our r is our 3/4. Well, 1 minus 3/4, this is indeed 1/4, which we can move upstairs as a 4. And lo and behold, we still get 3 to the 5th times 4 squared, which is still, not surprising, 243 divided by 16. So you can do that. Now in practice, we almost never need to reindex. The only thing to remember is just make sure you have the right first term, because that's what you need. Now since we have a little bit of space here, let's do a fun aside. So this is sometimes people like to sort of like, what? That doesn't make any sense. So what is 0.999999? Okay, well, let's talk about that. Now, one way to think of 0.999999 is you can say, well, look, this first 9 here, that's like 9 over 10. The second 9 here would be 9 over 100 because it's sort of in the hundredths place. The next one is 9 over 1,000. The next one, well, 9 over 10,000, which is really what? Well, what you really have is like, that's 9 over 10 plus 9 over 10 squared plus 9 over 10 cubed plus 9 over 10 to the fourth plus ... See, what we've done is we've translated a number into a sum. And these two are the same, right? Because they have the same, this says you put 9s in all the decimal places, and that's what this sum is doing over here. Now, what kind of sum do we have? Well, if you look at it, you really have 9 over 10 plus 9 over 10 times 1/10 to the 1 plus 9 over 10 times 1/10 squared plus 9 over 10 times 1/10 cubed and so forth. So what we have is we have something that's geometric. And to get from one term to the next, you're multiplying by 10 downstairs. So what's the rule? What does this equal? Well, according to the rule, this is the first term, which is 9 over 10. Divide that by 1 minus, what do we multiply by? Well, what we're multiplying by at every stage is 1/10. So that's 9 over 10 downstairs. 1 minus 1 over 10 is 9 over 10. And if you clean it up, you get 1. So 0.999999, so forth and so on, is 1. And that's a way to argue it with geometric series, because you can see at every stage we have equality. All right, so it's kind of interesting because a lot of people are convinced, wait a second, no, these should be different numbers because they have different decimal representations. Well, it turns out that there's a caveat to that statement, and the caveat is, and except for 0.99999999, if you have a bunch of 9s on the end, well, that's actually not a different number, because you can place a bunch of 9s on the end with a bunch of 0s on the end. Just sort of go up a little bit. All right, so, okay, fun aside. Back to serious stuff. All right. Find the values of b so that the sum from 0 to infinity of 1 plus b to the n divided by 1 plus b to the n equals 5. Now, if you're just listening and not reading, you might say, wait a second, you said something which is nonsensical. Well, right. Well, that's why you got to look. See, parentheses matter. 1 plus b to the n versus 1 plus b all in parentheses to the n are slightly different. Now, if you saw this problem today, you would say, okay, it's geometric. But you may not always see this problem today, so we want to learn how to spot in the wild. So we're out in the wild, we see a problem like this. What's the clue that we're doing something geometric? Well, the clue is when you see the exponents. So when you see n up in the exponents, that's a sign that you're probably doing something related to geometrical series. All right, so we're doing some geometrical stuff. So what are we going to do? Well, we want to rewrite this in a better way. So the 5 must be the 5. So let's see. We can say this is the sum from 0 to infinity. And now we're going to take advantage of a really powerful tool. It's called algebra, and in particular, addition. We can break up over addition. So I can say, look, this is 1 over 1 plus b to the n plus b to the n over 1 plus b to the n. Okay, so far, no big surprises. So this is the sum, n equals 0 to infinity of, now the first term, I can just write that as 1 over 1 plus b to the n. The second term, I can think of as b over 1 plus b to the n. Now, so far, we're okay, but there is a small catch. How do we handle this? Well, the answer is, really, when we have an infinite sum, if both the sums converge, we can split it up. So let's assume that they both converge. If they didn't converge, we wouldn't be able to do anything. So 1 over 1 plus b to the n plus another sum. b over 1 plus b to the n. Now we have a nice geometric sum. In fact, we have two nice geometric sums. The first sum will become 1 over 1 minus 1 over 1 plus b. Why? Well, n equals 0. The 0 power gives us 1, so our first term is 1. And our ratio, what we're multiplying every time, is 1 over 1 plus b. Our second term is very similar. Again, our first term is 1. Then we're going to get 1 minus b over 1 plus b. All right. Well, if we multiply top and bottom by 1 plus b in both of the terms, we're going to get 1 plus b upstairs. Divide that by 1 plus b minus 1 plus 1 plus b. Divide that by 1 plus b minus b. Well, what does that become? Well, here we get 1 plus b. Divide that by b, because the 1's cancel, plus 1 plus b divided by 1. The b's cancel. And remember that that's going to be equal to 5. Okay, so now that's what we have to solve. And that's a lot easier. So we started with this really complicated thing, use what we knew about geometric series to get down to a simple algebra type relationship. Well, to solve, let's take this equation and let's multiply both sides by b. So if we multiply both sides by b, what do we get? Well, here the b will cancel, so we'll just get 1 plus b, plus here it'll be b times 1 plus b, and on the other side we'll get 5b. So we'll get b squared, because the b times the b, then we'll get plus a b plus another b, and let's bring that 5b across, so that'll be minus 3b, and then finally plus 1, and that should equal 0. So b squared minus 3b plus 1 equals 0. Now, what comes next? Well, the next thing for us to do is factor. But this is one of those rare times. It doesn't factor. So what do you do then? Give up? Never. No, we're never going to give up. Well, we've got to come up with something else. Well, we have something else. If we have a quadratic that doesn't factor, we use our formula. So it says, take the negative of what's in front of that term, so that would be 3, plus or minus the square root of that term squared, 9, minus 4 times what's in front of here, times what's in there, so minus 4, all over 2 times what's there. So you get 3 plus or minus the square root of 5 over 2. And so that should be the answer. Now, technically, what should we do to be very safe? Now, what do I mean by that? Well, we have two possibilities. 3 plus the square root of 5 over 2, and 3 minus the square root of 5 over 2. Now, what you want to do if you want to be very safe is you ask the question, what's true about 1 over 1 plus b? Is it between negative 1 and positive 1? If it is, then that's good. And what's true about b over 1 plus b? Is that also between negative 1 and positive 1? And if it is, then you're okay. Now, that requires a computation, but it's not the easiest computation with these. So I'll just tell you that in this case, they both work. So we get two possibilities. Now, on an exam, we would say, well, that they both work, or would give you something a little bit more fun to work with. All right, well, let's do a little bit of a physics application. Okay. So, we're going to do a bouncing ball. So a ball drops from an initial height of 2 feet. Okay, all right. So it's a ball. So here we go, 2 feet, and it drops down. And then it bounces up to 3/4 of the height to which it fell. And after that, well, again, it turns out balls will fall down again. And then it's going to go up again and go down again and go up again and go down again, right? And it's going to keep doing that for a very long time. Okay, so we have the ball doing that. All right, now if it keeps doing this, how much distance will the ball travel before stopping? Now, you shouldn't read this as like it's moving horizontally. You should think of this as time. So it's moving up and down with time. Okay, so let's figure this out. So let's talk about the first drop. Now the first drop here, how far did the ball travel? Well, the answer is it started 2 feet up. So it went 2 feet. All right, good. Now, let's do our next one. How far will it travel here? Well, it's going to bounce up to 3/4 of its original height. So, if it's 3/4 of 2 feet, how high up will it go? Well, it's going to go up 3/2, or 1.5 feet. So that's how high up it goes. But of course, after it goes up, it's going to do what balls often do, which is go down. So it goes up and down. So the whole effect will be how far? Be 3 feet. Now, how about the next one? This is the key, because eventually we're not going to keep doing this forever and ever. So, if we think about this current one, so this was at 1.5 feet, right? Or, if you like, you can think of it as 3/2. Now, this is going to go up to 3/4 of that height. So, what we're going to do is we're going to take 3/2 times 3/4. That's how high up it will go. And then we're going to double that. Because after it goes up, it has to go down. Now, what does that turn out to be? Well, 3/2 times 2 is 3 times 3/4. So I can think of this as 3 times 3/4. And if you think of it in that way, you might say, well, that kind of makes sense, right? Because it says, whatever your previous distance was, you take 3/4 of that. Because if it went up to a certain height, you only go up 3/4 as high, but you're still going to go up and down. So what about this next one? Well, you take 3/4 of the one in front of it. So that would be 3 times 3/4 squared. How about the one after that? Well, that would be 3 times 3/4 cubed, and so forth and so on. So what do we have? Well, what we have is the following. It's a pattern, right? So it's 2 plus 3 plus 3 times 3/4 plus 3 times 3/4 squared plus 3 times 3/4 cubed and dot dot dot. And of course, remember, dot 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 is a fancy way of saying the pattern continues. So whatever we see at the start, it's going to keep doing that forever. All right. Now, is this geometric? No, not quite. Why is it not geometric? This pesky 2 sort of throws a wrench into things. So we have to say, okay, how do we handle it if it's not geometric? Well, but it's basically like geometric except for that 2. So here's the thing, is you can break things into parts. So say, look, this part, This part is geometric. And now we can apply our tools. And the 2, well, that'll be 2 plus whatever the rest of it becomes. Now what will the rest of it become? Well, we have the 3. That's our first term, right? And then we're going to divide that by 1 minus, what are we multiplying by? Well, at each stage, we're multiplying by 3/4. So 1 minus 3/4. So that becomes 2 plus 3 over 1/4, which is 2 plus 12, which is 14. And therefore, it'll travel 14, and if we want to throw in units, feet. So, even though it is bouncing up and down, and it's going to bounce up and down infinitely often, it's not going to travel an infinite amount of time. It's only going to travel 14 feet. It's one of these things, there's these wonderful paradoxes that say, how is it possible that you might have infinitely many things happen, but you only end up with a finite total? And this dates back to ancient Greece, where they had the famous sort of paradox of Achilles, who was this very fast runner. And so let's say here's Achilles, and very fast runner. So he's got some good feet on him. And he was going to race a tortoise, which tortoises, in case you don't know, are not known for speed. But the idea was, look, the tortoise has a head start. And before Achilles can win, he has to get to where the tortoise started. But then the tortoise, it's moved a little bit. And now Achilles has to catch up again, and again, and again, and again, infinitely often. And they said, look, if he has to do it infinitely often, he can never pass. Well, but that's the thing. You can add up infinitely many things and still have it be finite. So there really is no paradox. All right. How long will it take? Same problem, right? We still have the ball dropping. Now, there's a little bit of physics here. It says, look, the initial drop, it takes 1/4 root 2 seconds to land. And, well, we get the square roots just because velocity involves squares, and there's all these other various things. Okay, so that's the first drop. So again, we have our same ball still dropping, but now instead of our we can ask ourselves the question, well, how long will it take? Is that ball going to be bouncing forever, or will it stop bouncing? Well, eventually it'd be like, and then stop. Ball's still. Okay, so the initial drop, 1/4 root 2. The second one takes 1/4 root 6. How do I know that? Because it says it right there. And each subsequent bounce takes 1/2 root 3 times as long as the previous bounce. So that says, look, the next one here, you take the previous bounce, 1/4 root 6, you multiply it by 1/2 root 3. The next one, well, you take the previous one, and you multiply it by 1/2 root 3. So that's like 1/2 root 3 squared. And so forth and so on. And so what you end up happening here is we get another geometric series, but of course with really bizarre looking terms. ... So we get that the total amount of time, 1/4 root 2 plus 1/4 root 6 plus 1/4 root 6 times root 3 over 2 plus 1/4 root 6 root 3 over 2 squared, ... Again, the first term, that's going to be its own little thing, 1/4 root 2, plus the rest of this is geometric. So, the first term, 1/4 root 6, divide that by 1 minus, we multiply at every stage, which is root 3 over 2. And, yeah, here we go. Good enough. But the point here is that's going to stop in finite time. It's a finite number. It's some number. And if we were in a high school class, we'd be like, oh, cool, we get to rationalize our denominators. But that's not why we came to university. We came to understand the beauty of it. And we see it. All right. So geometric series, they're really cool because we can actually find the value for a geometric series. And we're going to see that there's only 3 cases where we can find value. So one of them is geometric, and here's the other one, telescoping. Now I said there were 3. The third one we're going to have to wait a long time for. So right now there's just 2. So what's the telescoping sum? It's kind of sort of has the flavor of what happened with geometric. You might remember in geometric we said, hey, we can cancel a lot of the middle terms. Well, here we're going to do something very similar. We're going to telescope. What's going to happen is we're going to take the first term and the last term, maybe the first couple of the last couple, and the middles are all going to go away. Now, why do we call it telescoping? The way I like to think about it is if you ever watch some of these like pirate movies and they pull out their telescope to look at the ship coming in the distance. They have that thing that extends. Well, it also collapses. So one way you can think of telescoping sums are collapsing sums. All right, so here's an example. Find the sum 1 to infinity of 1 over n times n plus 1. Now, not so clear what to do, not yet, but suppose we had a different question. Suppose you were asked the following. Suppose you're saying, integrate 1 over x times x plus 1 dx. What would you do? Because you can think of a sum as being a lot like an integral. It's all about adding things up. So, when we saw this kind of problem, what technique did we use? Do you remember? It's been a while. It's hard to remember things. You know, we have some partial memories of what we did back then. Do you remember? Yes, partial fractions. Yes, aha, partial fractions. So, well, look, it's the technique so nice, we can use it twice. If it works here, it can also work here. Because really, what's the goal of partial fractions? Partial fractions isn't about integration, it's about rewriting things. So, what will we do? Well, in the case of an integral, we'd say, well, look, let's 1 over x times x plus 1. We break that as something over x plus something over x plus 1. Well, we're going to do the same thing here, except the only difference is instead of an x, we'll use the n. 1 over n times n plus 1 is something over n plus something over n plus 1. Clear your denominators. So 1 equals a times n plus 1 plus b times n. Now, remember what we did here. There were a couple of options. One was, solve for a system of equations, but a better option was make good choices. So, what's a good choice for n? You might say, aha, n equals 0, but wait a second, you're not allowed to n equals 0. No, don't worry about that. Ignore that. Focus on this. And just say, what's a good choice for this relationship? N equals 0, great choice. If you do that, you'll come to the conclusion a equals 1. Another good choice is n equals minus 1, because then that term drops out. B times minus 1 is minus b, so minus b equals 1, or b equals negative 1. So, what do we have? Well, this is the sum, n equals 1 to infinity, of, it's a over n, so 1 over n, minus 1 over n plus 1. Now, I want to be a little bit careful here, because if you are a little bit sloppy, you might do something dangerous, which is to say, let me break this into 2 sums, because we did that before with the geometric sums. The reason we did it before with the geometric sums is that the individual sums still converged. That might not be the case here, because that's not the case here. So you want to be a little bit careful here. So let's think about what's happening. So we start writing down some terms. So we say, okay, well, this is 1 over 1 minus 1 over 2. That's the first term. Then the next term is 1 over 2 minus 1 over 3, because this is the n equals 1 term. Here's n equals 2. The next term after that is 1 over 3 minus 1 over 4. Okay? That's n equals 3. Next term, 1 over 4 minus 1 over 5. Okay? And you might say, well, when do you stop? You don't have to stop. You can keep going until you get bored or you run out of space. But why would we ever get bored doing math? This is great stuff. So, we're running out of space. Okay, so we'll stop here. Now, what's the idea? Well, the idea is that terms cancel. See, the halves cancel, the thirds cancel, the fourths cancel, the fifths cancel, the sixths cancels, the seventh would cancel with whatever comes next. And what doesn't cancel? Well, the only thing that doesn't cancel is the 1. So we would say equals 1. Right? Good. Now that is the right answer, but you want to be a little bit careful. A little bit careful. So what should you actually do? Well, remember, the way we do an infinite sum is we look at a finite sum. So what will end up happening is we really go and we have the first couple of terms. So, and then we go up to some stopping point. So I'll come up here, I'll call it capital N is where I stop. All right? So this is my 1, 2, capital N. So this is my partial sum. And what happens is we get cancellation, 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 and the first term doesn't cancel, and the last term doesn't cancel. So that our partial sums look like 1 minus 1 over n plus 1. And now we say, okay, what happens? Well, this part goes to 0 as n gets large. And therefore, we can say that Sn, our partial sums, goes to 1. So that's why we can say, yes, this does in fact converge. So you want to pay attention. Look what happens on the end. Look what happens on the end. All right, let's do a couple more examples. Okay, I promise we're almost there. We're almost there. All right, here's another sum. K equals 1 to infinity, log of 1 plus 1 over k. Okay, what happens? What happens here? Well, at first glance, this doesn't look like a telescoping sum. Now you might say, well, yeah, that doesn't look like a telescoping sum because I don't know what telescoping sums should look like. So let me pause for a second and talk about what we mean by a telescoping sum. So a telescoping sum is something that really can be rewritten in the following form. So it looks like a sum from k equals some starting value j to infinity, and then you have, I'm going to be very, very generic here, and I apologize for this, but you have f of some value k, so this is like your a sub k, minus your f of k plus a shift, L. So L here is a shift. And what's going to happen is when you do this, you're going to get that this term here will cancel with a term L steps down. So it's the shift that gets the cancellation. So this causes the cancellation. All right, so that's what we mean by telescoping, is we really want to be able to write something that looks like that. Now, if you go back to the previous problem, which I know was a long, long time ago, what happened was, you see how it was 1 over n minus 1 over n plus 1? So our function was just, our function of, here it's k, we could call it n, was 1 over n. The shift was by 1, which meant that we got cancellation with the one term away. And you can see that. See, it's like one term. Sometimes you have to go a couple terms to cancel. And, well, quiz problems, you'll see those. All right, so that's what a telescoping sum looks like. Now that I've said that, that's what a telescoping sum looks like, you're going to look at me and say, that's definitely not a telescoping sum. Not yet. But what can we do? We can rewrite it. Okay, so let's think about this expression. So this is the sum, k equals 1 to infinity, of, on the inside I can write this as k plus 1 over k. Because I can add those together, get a common denominator. Now, when you have that, what do you get? Well, this becomes sum k equals 1 to infinity log of k plus 1 minus log of k. Now, it does feel like a telescoping sum, right? Because we have a subtraction, and what's happened is that there's a shift. Okay, so what happens? If you write this out, you get the following. You get log of 2 minus log of 1. That's the first term. Plus, next term, log of k equals 2 would be log of 3 minus log of 2. The next term, after that, what would that be? Well, plus log of 4 minus log of 3, and so forth and so on. Now, what's the answer? We'll say, aha, look, it's clear, right? The log of 2's cancel, the log of 3's cancel, this log of 4 will cancel later on with something. Everything cancels, we're left with log of 1, and log of 1 is 0. So that must be our answer, right? 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 No, that's not our answer. It turns out it's not 0. Now, that seems somewhat unsatisfying, just for me to say it's not 0. How can we see that? Well, here's one way to see it. Natural log of 1 is 0. If I have anything, natural log of anything bigger than 1, it's actually positive. Each term in here is positive. And if I add them all together, I shouldn't end up with 0. I can't add up infinitely many positive numbers and get 0. Something is wrong. Okay, so here's that subtlety. So let's talk about what's actually happening here. So we get the following. We have the first term, we have the second term, and so forth and so on. And then what's going to happen is at the end, we're going to get a partial sum, right? We're going to look at our Sn, our partial sum. So that would be corresponding to what? N plus 1 minus natural log n. Now what happens? Well, what happens is we do get lots of cancellation, but we don't get everything canceled. So we have a first term, which is that minus log of 1, and that's 0, and this last term, which is natural log of n plus 1. Now that's 0, so it means that our partial sums look like natural log of n plus 1. And what happens to natural log of n plus 1 as n gets big? It goes to infinity. So this is a sum where the parts are very small. In fact, you can see this is getting close to natural log of 1, which is 0. So even though the parts are very, 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 very tiny, very small, when you add them all up, it gets infinitely large. Now, what's the moral here? Well, it turns out for telescoping sums, you have to be careful. So, if your function f of n goes to 0 as n goes to infinity, then you only need to look at the first few terms. So, only need the first few terms. Because what's going to happen is that the n, see like here, the n part was that natural log n plus 1. When the fn goes to 0, that says that when you telescope, you get a couple terms at the start and a couple terms at the end. The couple terms at the end, not important. Okay. So, if your fn goes to infinity, as n goes to infinity, then the sum goes to infinity. Now, you might notice there's a lot of space in between. So if fn goes to some constant c, where c is not 0, then you need to pay attention to both start and finish. So be careful. Now, you might say, could that ever happen? And yes, in fact, we put it on an exam once, and the students did not like it for some reason. And here's an example. Sum k equals, say, 1 to infinity of cosine squared pi over k minus cosine squared pi over k plus 1. Now, if you run through and ask what happens, see, this is like our cosine squared pi over k. That's like our function of k. What's happening to that is that at the end, it goes towards 1. So you have to be very, very careful. And it turns out, I believe, if I remember right, this equals 0. So I'll let you work that out. Okay, if f n goes to c, got to pay attention to both start and end. If the terms go to 0, then you only need the first few terms. Life is good. Everything does cancel like you expect. Terms go to infinity. All right, things blow up. All right, so that's telescoping. I think we have one last one for today. All right, so find the sum L equals 1 to infinity of L over L plus 1 factorial. And, well, we've been here a long time, so let's not dilly-dally. Hint, add 0. Well, what do we want to do? Well, we really want to clean this up. Now, think about what L plus 1 factorial looks like. L plus 1 factorial looks like you start with L plus 1, then you multiply it by L, then by L minus 1, and you go all the way down 3 and 2 and 1. So I'd really like to get some cancellation. But see, it's kind of canceling in a weird place. It's canceling in the second term. I'd really like it to cancel the first term. Because if I can cancel the first term, it looks better. So I say, well, it would be, if I want to cancel the first term, I can't have an L. I really need an L plus 1. And then I can cancel the first term. But I can't just add 1. But I could add 1 and subtract 1, which is like adding 0. That's what the hint meant. Okay, cool. So this becomes the sum, L equals 1 to infinity of, I can think of it as L plus 1 over L plus 1 factorial minus 1 over L plus 1 factorial. All right? So there's our sum. Now, notice if I take L plus 1 divided by L plus 1 factorial, I'm canceling that leading term. What's left is a factorial. So this is the sum 1 to infinity of 1 over L factorial minus 1 over L plus 1 factorial. Now we're back into something that looks like telescoping. We have some function, in this case L, and here's another function, same function, but the index has been shifted by 1, which means we'll get cancellation. Do we need to worry about the end? Well, ask yourself the question, what happens to this as L gets big? So if I divide 1 by a huge number factorial, does that go to infinity? Does it go to 0? Does it go to somewhere in between? Well, factorials get huge, so it's 1 over a huge number, so that's going to 0, which means I only need to pay attention to the start, which is good news for us. So this is, if you write this down, 1 over 1 factorial minus 1 over 2 factorial plus 1 over 2 factorial minus 1 over 3 factorial, and so forth and so on. And lo and behold, at the end, cancel. The thing that won't cancel is that. And so we end up 1 factorial is 1, and life is good. All right, cancel, so forth and so on. Okay, and that's it for today. Big day. Well, there's a lot for us to add up, right? So it takes a while. And well, we'll pick it up again next time. All right, see you then. Bye.